very good day, students and friends. Welcome to this series on differential calculus. We begin with the concept of limits. Limits of a function forms the basis of both differential and integral calculus. The prerequisites for this discussion is understanding of functions and their graphs. There should be some basic understanding on graphing of the function. Of course, those who are not familiar with it, the way within this series the examples are taken, the basics of graphing will be also covered. So now let's begin with limits. Let's enter into the classroom. So let's begin with the concept of limits. First, let us consider this function. F of x is equal to x plus 1. Now let us consider the behavior of this function at x equal to 1. Now we know that this function at x equal to 1 gives us the value 1 plus 1 equal to 2. So how do we graph a function? We plot the domain or the values of x on the x-axis and the values of the function on the y-axis. So we also denote y is equal to f of x for this reason. So now let us look at the graph of this function. From the concept of straight lines, we know that this line y is equal to x plus 1 is a straight line which has a slope of 1 unit and it cuts the y-axis at 1. Now we want to evaluate the function at x equal to 1 at this point. At x equal to 1, the value of the function is 2. So I want to study function around 1. I want to see when I come close to 1, what will be my value of f of x. So let us look at this. I draw a table. This is x and this is f of x. Now just less than 1. Let's say I have the value of 0.9. What will be the value of f of x? 0.9 plus 1, 1.9. Now I go closer to 1, 0.99. This is much closer to 1, right? So the value of f of x will be 1.99. Next, I'll go much more closer to 1, 0.999, and the value of f of x is 1.999. What I am observing is, as I approach closer to 1, value of the function f of x is getting closer to 2. So you can see f of x is going closer to 2. We say for this, limit x tends to 1 minus f of x is equal to 2. What it means is, as x approaches 1 from the left, when we say minus, we say we are approaching 1 from values lesser than 1. So we say as x tends to 1 minus. So minus indicates that the value of x, we are approaching 1 from values lesser than 1. Now as x tends to 1 minus, f of x tends to 2. It is approaching 2, and here of course it is approaching 2 from values lesser than 2, but we don't bother about that. We worry about x, whether we are approaching from the left or the right. Similarly, now let us consider this. We approach x equal to 1 from the right. So let us say x is 1.1. Then what will be the value of f of x? 1.1 plus 1, that is 2.1. Again, what is now let us consider x as 1.01. Then the value is 2.01, value of f of x. Now let us come more closer to 1. 1.001. The value of f of x is 2.001. That means what are we seeing? As x is approaching closer to 1 from the right, that means the values of x, we are approaching the value of x equal to 1 from numbers greater than 1. So we find that f of x also approaches the value 2. So in this case we say limit x tends to 1 plus f of x is equal to 2, or we say as x tends to 1 plus f of x tends to 2. Tends to. Again, I want to emphasize one very important point. When we say tends to, it means the value of x is not equal to 1. It is approaching 1. And the value of function f of x is approaching 2. It is not equal to 2. So limit, although we write an equal to sign, limit x tends to 1 plus f of x equal to 2, it does not mean that the function value f of x is equal to 2. It is f of x is tending to 2. So this is example 1. This limit x tends to 1 minus f of x is equal to 2. We call it as the left hand limit as x tends to 1. Left hand limit as x tends to 1. Now this limit x tends to 1 plus f of x equal to 2 is called as the right hand limit at x equal to 1, or as x tends to 1 plus. Next, we'll go ahead to look at another example. In the previous case, the function was defined at the point x equal to 1. Now let us consider another example. F of x is equal to x square minus 1 by x minus 1. In the domain of definition of this function, x equal to 1 does not exist. That means this function is not defined for f is not defined at x equal to 1. Why? Because at x equal to 1 you get a division by 0. There can be 0 in the numerator, no problem, but when you have a 0 in the denominator, the function is not defined. The domain of definition of this function is all real numbers minus 1. Okay, so we will now study the behavior of this function at x equal to 1. So let's move further. So I'll simplify this function x square minus 1 by x minus 1 as x plus 1 into x minus 1 by x minus 1. Remember, at x equal to 1 the function does not exist. However, other than x equal to 1, we can cancel off these two factors. Thus we get pretty much like the previous function. So now let's plot this graph. F of x is equal to x plus 1 for all values of x other than x equal to 1. At x equal to 1, here, unlike the previous case, f of 1 here is not defined. There is no definition. So function value does not exist. However, other than x equal to 1, the function values exist. And let's look at the shape. So very carefully, I don't start at 1. I start just at the left of 1. You can observe carefully. This will be the graph of the function. But at x equal to 1, function is not defined. So I don't plot the function at that point. And then again, at to the right of 1, this will be the graph of the function. So the function is not defined at x equal to 1. In any case, now let us consider as x approaches 1 from the left. By the same arguments of the previous example, we can see that the function value is approaching, the value of the function is approaching the value 2. When x is approaching 1 from the left, function is approaching the value 2. And when x is approaching 1 from the right, the function value is approaching 2 again. So in this case, again, as x tends to 1 minus, f of x tends to 2. So we write this as limit x tends to 1 minus f of x is equal to 2. Again, as x tends to 1 plus, f of x tends to 2. So we write this as limit x tends to 1 plus f of x is equal to 2. So remember, again I am emphasizing, although we write limit of a function as x tends to a particular value as 2 in this case, it does not mean that function is equal to 2. The function value cannot be 2 here, because at x equal to 1, the function does not exist. The range of this function, if we go back to the basics of the function definition, the range of this function is equal to r minus 2, because the value 2 cannot exist within the range. So what do we observe in the two cases? In both the examples that we discussed, we observed that in both the examples, the left hand limit, LHL for brevity, is equal to the right hand limit. We will call the right hand limit as RHL. So left hand limit is equal to right hand limit in both the cases. Left hand limit of f of x is equal to the right hand limit and was equal to 2 in both the examples, example 1 and an example 2. Both were equal to 2. When left hand limit is equal to the right hand limit, we say that the limit exists. Limit of the function f of x at x equal to 1 exists. If left hand limit is not equal to right hand limit, then we say that the limit does not exist. Now let us take an example, another example to illustrate this one. Now let us consider f of x is equal to modulus of x minus 1 by x minus 1. The modulus function. How does the modulus function behave? Modulus of x minus 1 will be equal to x minus 1 when this x minus 1 is positive. That means when x is greater than 1. And the modulus of x minus 1 will be minus of x minus 1 when x minus 1 is negative. That means when x is less than minus 1. This is the definition of modulus. So this is what we get. And at x equal to 1, it is 0. The numerator is 0. However, the denominator is 0 is not acceptable. So again, the domain of definition for this function is r minus 1. That means x equal to 1 cannot be within the domain of definition. So for x equal to 1, the function is not defined. So we get here. Now we can write this f of x, this function, in piecewise form as when x is less than 1, we write this as minus of x minus 1 by x minus 1. This becomes equal to minus 1. This is when x is less than 1. When x is greater than 1, modulus of x minus 1 is x minus 1. So you get x minus 1 by x minus 1, which is equal to 1. So in essence, we get f of x is equal to minus 1 when x less than 1, and f of x equal to 1 when x is greater than 1. Now let us see the plot of this function. When x is less than 1, f of x is minus 1 and it is constant. So the constant function, when x is less than 1, f of x is equal to minus 1, and when x is greater than 1, f of x is equal to 1. But at x equal to 1, function is not defined. We want to again study limit at x equal to 1. So as is approaching 1 from the left, what we see, the function values are all they equal to minus 1. So here in this case, we get limit x tends to 1 minus. That means as x tends to 1 from the left, the function is, the value of the function is minus 1. Similarly, when x tends to 1 plus, that means we approach 1 from the right of 1. We are on the number line, we are approaching 1 from the right, and we observe that the function value is constant and is equal to 1. So we write limit x tends to 1 plus f of x equal to 1, and function is not defined at x equal to 1. So we make important conclusions from these three examples. The first conclusion is that a function f of x may or may not be defined at a point. In the first two examples, we considered at x equal to 1. So a function may or may not be defined at x equal to 1. Yet the limit of f of x can exist. So in the examples 1 and 2 that we discussed, the left hand limit at f of x and the right hand limit of f of x at x equal to 1 was equal to 2. So left hand limit equal to right hand limit is equal to 2, and we say the limit exists and the limit value is equal to 2, and we write as together, when we remove left hand limit and right hand limit, we write this as limit f of x as x tends to 1 is equal to 2. When we write limit f of x as x tends to 1 equal to 2, it automatically implies that the left hand limit exists, the right hand limit exists, and both are equal. Second conclusion is that, like in the case of example 3, left hand limit was not equal to right hand limit. Then we say the limit of f of x as at x equal to 0 does not exist. And if we write this as limit x tends to 1 f of x, it will not be equal to anything. We just have to say that this does not exist. We'll continue with further concepts of limits in the next class.